Now sulfur. So first it is allotropes of sulfur. There are two allotropes: alpha sulfur, beta sulfur. Alpha sulfur is yellow rhombic. Beta sulfur is monoclinic structure. Just remember this. And the alpha sulfur is stable at room temperature, and at 369 Kelvin transforms into beta sulfur. And this 369 Kelvin temperature is called as transition temperature, where both alpha S and beta S are stable. Okay, and now alpha sulfur is yellow colored. It is formed by evaporating solution of rolled sulfur in CS2 carbon disulfide. Okay, it is insoluble in water, dissolves to some extent in benzene, alcohol, ether, organic solvents, and it is readily soluble in carbon disulfide. Just remember. Okay, beta sulfur, it is colorless and needle shaped crystals when it is formed from alpha S to beta S. Both exist in form of acid, and it is crown shaped, right, like this. S6 is also there, which is chair shaped, and S2 is a very popular form which is formed in vapor state. It is paramagnetic in nature, and it exists in very high temperature, 1000 Kelvin. Sulfur dioxide preparation. There are three methods: general method, industrial method, lab method. Now general method is what? Here sulfur is just burned in air, right, to give SO2. Now it also forms SO3, like 6 to 8% SO3 along with this when sulfur is burned in O2. Now lab method. What is the lab method? It is readily formed by treating sulfides with the dilute sulfuric acid. Now what are sulfides? These ions, SO3 2 minus, which when reacted with H plus from H2SO4, you get SO2 plus H2O. Water is also removed out from here. H2O is removed out. Industrial method is from ores, and especially the sulfide ores. Like when you do roasting of, like suppose FeS2 is an ore of sulfide ore. Now you just roast it with oxygen, you roast, so you get SO2, and byproduct as Fe2O3. This is as a byproduct. So these three are methods of preparation. Generally is burning sulfur, or industrial is by roasting the ores. Here you should write roasting. And lab method is by sulfide ions in water, in acid. Sulfide ions in acid, water is removed, SO2. Now what are the reactions, different reactions? So first of all, when you treat SO2 with water, it transforms into H2SO4. When you treat it with base, it's not H2SO4. When you treat it with water, it becomes H2SO3, sulfurous acid. When you react SO2 with NaOH, that is the base, it transforms into Na2SO3. Right, this is here it becomes sodium sulfite. And if you again add excess of water to it, water and SO2, this is already aqueous solution, but when you add more of SO2 to Na2SO3, it transforms into NaHSO3, hydrogen sulfide. So yeah, SO2, when you react with NaOH, it becomes sodium sulfite. When it reacts with again excess of SO2, it transforms into sodium hydrogen sulfide. Now when SO2 is reacted with chlorine in presence of charcoal, it transforms into SO2Cl2. Now what is this? It is called as sulfuryl chloride. Sulfuryl chloride. So in presence of charcoal with Cl2, it gives SO2 Cl2, just remember. And in it oxidizes, right, this we use generally to oxidize, transforms into SO3, right. Now these were the reactions. So again, just revise. Preparation from general industrial lab. General is burn sulfur in air. Industrial is roasting of the ores, FAS2, and lab is from sulfide ores, right. Sorry, sulfide ores not, these are sulfide iron. It's not sulfide iron, it's sulfite iron, right. It is sulfite ions. When you sulfide ions you treat with acid, it gives SO2. Sulfide is this, right, this is sulfite. Now when you treat it with base, when you treat sulfite with acid you get SO2. So when you will treat it with base SO2, it will give you sulfite again, right, simple. So it will give you again sulfite, and when you treat it with excess of SO2 in presence of water, it will give hydrogen sulfite. Now when you react it with chlorine in presence of charcoal, it gives sulfuryl chloride SO2Cl2, and with water it gives sulfurous acid H2SO3. With O2 in presence of V2O5, it gives SO3. And these were the reactions you have to remember. Now moist SO2 is a very good reducing agent. It converts Fe3 plus to Fe2 plus, right. And very important test, which is decolorization of acidified KMNO4, right. This is used as a test for this SO2 gas. It's very important. It decolorizes the acidified KMNO4. Now some properties are written here about sulfur dioxide: colorless gas, pungent smell, soluble in water. Okay, SO2 is soluble in water, obviously it gives sulfurous acid. And this colorless gas, pungent smell, it liquefies at the room temperature under a presence of 2 atmospheres. Okay, pressure of 2 bar atmospheres it should be. In sulfur dioxide, when passed through water, it forms sulfurous acid. These are already done. In its reaction with water and alkalis, the behavior of sulfur dioxide is very similar to that of carbon dioxide. Now we come to sulfuric acid. It's prepared using the contact process. What is the contact process? In this process, the first step is burning of sulfur or sulfide ores in the air. We get SO2 from this. Now this SO2, we know it gets oxidized by O2 in presence of catalyst to form sulfur trioxide SO3. Now since this is a very highly exothermic reaction, delta H is negative here, and it's highly exothermic, so low temperature is favored here. But the temperature should not be so low that the rate of reaction also slows down. So the optimum case is here 2 bar and 720 Kelvin. Now the SO3 we got here, we just absorb it in concentrated H2SO4 solution to form oleum, and when this oleum is diluted we get H2SO4 again. Now SO3, if we treat with water, then it also gives H2SO4, but in this process, the contact process, we absorb it in concentrated H2SO4, right? Okay, see here in the reaction it is written, it transforms into oleum, and then after dilution it transforms into H2SO4. Now H2SO4, when treated with water, right, it gets dissociated into H plus and HSO4 minus, and this is highly forward going reaction. Like you can see Ka1 is greater than 10, but when HSO4 is again dissociated, H3 into H3O plus and SO4 2 minus, the Ka2 here is 1.2 into 10 to the power minus 2. It's pretty low from this one, right? So generally H2SO4 is dissociated into H plus and HSO4 minus more. Now here are the properties of sulfuric acid. It is colorless, dense, oily liquid. And here the chemical properties of sulfuric acid are due to low volatility, strong acidic character, strong affinity for water, and ability to act as an oxidizing agent. So what are the characteristic properties? Low volatility of H2SO4. Oily liquid, colorless and dense. Okay, it's low volatility, strong acidic character, strong affinity for water, and ability to act as oxidizing agent. Okay, now we already have seen this, and the acid forms two series of salts: normal sulfates like sodium sulfate and copper sulfate, and acid sulfates, hydrogen sulfate. We already knew that. Sulfuric acid, because of low volatility, can be used to manufacture more volatile acids from their corresponding salts, right? From metal salts we can use to form the acids which are more volatile than normal acids. Here X is halogen, right? So concentrated sulfuric acid is a very strong dehydrating agent. We already know that. Now we dehydrate the carbohydrates, right? Glucose, right? No, it's not glucose, it's a sugar. So when we pass through H2SO4, it removes water and leaves out carbon here. It's known as charring action on carbohydrates. It's very important. Hot concentrated sulfuric acid is a moderately strong oxidizing agent. This hot concentrated sulfuric acid, it in terms of intensity of dehydrating strength, it comes between the hot sulfuric acid comes between phosphoric and nitric acids. Okay, that is, phosphoric acid is more dehydrating than sulfuric acid, and sulfuric acid is more dehydrating than nitric acid. But both metals and non-metals are oxidized by concentrated sulfuric acid. Okay, these are some reactions. So H2SO4 is just making the sulfates, right? SO2 and CO2. Okay, with metals it is forming sulfates, and with all C it is giving out SO2 and water, H2SO4. With sulfur it forms SO2. With C it forms CO2 and also SO2, right?